Okay, so now we are ready to actually start running our experiment. And for that, we are going to do the following. So first, we're going to create our learning problem. What does that mean? Well, for a learning problem, at a bare minimum, you need kind of a train set with inputs and desired outputs, and a test set with the same inputs and desired outputs. To get the desired outputs, we need our teacher network to tell us, here's the input, this is the output I want. So to create your learning problem, you're gonna instantiate a teacher network with a given width and depth. You'll look at the instructions for the specific parameters. And then once you've created that teacher network, you can use that teacher network to generate a training set, input and output, and a test set, input and output. So that's your first step. Once you've generated your learning problem, then we'll run a sanity check. We'll see if sort of the data is reasonable and if the training code is working by doing something a little bit different from what we did last time. Last time, our first sanity check was to generate a teacher network and then literally copy paste that teacher network, same architecture, same weights, and train and see what you get. There, kind of intuitively, you don't even need to train. The student network is doing exactly what the teacher network is doing because it's a copy. Here, what we're going to do, our first sanity check, is to generate a teacher network, and then we generate a student network with the same architecture, so the same width, same depth, same nonlinearity, same everything else, but not the same randomly initialized weights, just a new set of randomly initialized weights. So the networks are the same shape, but their weights are different. And then we're going to train that. So you're also going to be asked to think afterwards in a written question about what the error should be at the beginning and what the error should be at the end of training when you do this sanity check. After that, we're ready to sort of really run the experiment we've been talking about, which is we're going to fit our deep teacher network, our complex function, with a single hidden layer network. And remember, the universal approximation theorem tells us that we can fit our complex function using a single layer network arbitrarily well, as long as we have enough hidden units. So we're going to now see kind of how much is enough. We're going to instantiate different student networks of different widths, train, and see how low we can get the error to be. So here's your code you're going to fill in. You note that there's a loop which iterates over different widths. At each point, we're going to generate a student network with a new width. We're going to train that student network, and then we're going to compute its test error once we've trained it. And that's going to give us sort of a curve. How well do you do as a function of how wide your network is? And then finally, we're going to do something sort of just kind of a quick and dirty extrapolation. What you'll find intuitively is the bigger the network, the lower you can get the error. So bigger network, more parameters, it's a more powerful function fitting model. And so intuitively, you should be able to do better with a bigger network. But how much better? So you're going to use the results of your experiment. You're going to have this sort of curve of error versus width. And you're going to fit a simple sort of predictive model. You give me a width, I tell you what's the error of that network going to be. A really simple model, which we don't expect to be, perfect, but it'll just give us kind of a rough calculation. We're going to build this model using NP's polyfit function. You'll fill in some code here. And then you're going to use the model to try to predict how wide does the network need to be in order to get a given low error rate, which we'll tell you about. We'll give you the specifics in the code. And this will give us an idea. The universal approximation theorem says you need a very wide network to fit a complex function. How wide? Here's an estimate. And you'll see if that width is reasonable or not. Reasonable, I mean, to use a shallow network as practically speaking, as a function fitter in this case.